Hey Thinksters, and welcome to today's coffee break Python. Today we are going to. I'm still in this Google FooBar challenge. I got invited to participate in the Google FooBar challenge. I think it's a hiring process for upcoming Google employees, and so I thought while I'm going through the challenges, I just share it with you. I do some screen capture. So I don't know the challenge yet. Okay, so I learn about the challenge as you do. So it's actually, you should be a bit more patient with me. So because I will go through the coding challenge as you. So I will read everything as you read it and hear about it the first time. So I will try to solve it online and until we have a solution. So I don't know how long this video will take. Just it takes as long as it takes to finish this this lesson. Okay, so if you participate in the Google challenge, you will get access to this share, and I guess it's a virtual machine somewhere hosted on the Google data center, and it just works as a virtual machine. So like Linux type share access, you can see what is in the directory. We have two files, the file journal and the file start here. You can type in help, and then you can see which commands you can use. So it's like a restricted set of Linux commands, you can say, with some specific commands for this coding challenge. So for example, if you type status, then you will get your current status, okay? And you see there are 5 levels which you have to pass in order to, I guess, qualify to be hired by Google. And we are currently at level 2. 50%, so we have solved one challenge of level 2, but I guess there are like 2 challenges per upcoming level. Maybe there are even more challenges for the higher level. I don't know yet. Okay, so this is our home directory. Now we have to check what is in there. Okay, and you can output files in the share by using the cat command. Cat. Let's open the start here file. And yeah, here they tell us type request. To request the challenge, type help for a list of commands. Let's check what is in the journal file. Success. You've managed to infiltrate Commander Lambda's evil organization and finally earned yourself an entry-level position as a minion. Okay, so I think we have already seen this, right? I will move this display. And okay, so let's start the next challenge. Are you ready? I am. We type request to request the next challenge. So now it requests the next challenge, and we have 72 hours to solve this next challenge. And this one is like 2 days, 23 hours, 59 minutes, 51 seconds. Okay, the challenge is, you got the guards to teach you a card game today. It's called Fizzbin. Sorry. Okay, we have Fizzbin. It sounds like Fizzbuzz. It's kind of pointless, but they seem to like it, and it helps you pass the time while you work your way up to Commander Lambda's inner circle. Okay, let's check what is in our directory now. Okay, we have a new, we already had these 2 files, but now we have a new file. Please pass a new folder. Please pass the coded messages. Okay, so let's cd into this folder. And let's check what is in this folder. Okay, we have like 4 files. This is similar as the coding challenges before. We have 4 files, one solution for the Java code, one solution for the Python code. We are going to use the Python solution here. Then we have some constraints in the README file. And let's quickly start with the README file. As a coder, you should always start with the README file. Okay, and I would just take this whole thing and copy paste it so that I can use it later. Copy. Okay. Good, and let's read this. Please pass the coded messages. You need to pass a message to the bunny prisoners, but to avoid detection, the code you agree to use is obscure, to say the least. The bunnies are given food on standard issue prison blades that are stamped with the numbers 0 to 9 for easier sorting. And you need to combine sets of blades to create the numbers in the code. The signal that the number is part of the code is that it is divisible by 3. You can do smaller numbers like 15 and 45 easily, but bigger numbers like 144 and 414 are a little trickier. Write a program to help yourself quickly create large numbers for use in the code, given a limited number of plates to work with. You have L, so this is, I guess this is the important part. You have L, a list containing some digits 0 to 9. Okay, we have a list of digits. Write a function solution L, which finds the largest number that can be made from some or all of these digits and is divisible by 3. Okay, this function solution L finds the largest number that can be made from some or all of these digits and is divisible by 3. Okay, so in the most extreme case, we sum over all numbers in the list, and if the result is divisible by 3, then this would be our final number. If it is not possible to make such a number, return 0 as the solution. L will contain anywhere from 1 to 9 digits. The same digit may appear multiple times in the list, but each element in the list may only be used once. Ah, okay. So we need to remove duplicates, kind of. Okay, we can, test cases are, your code should pass the following test cases. And yeah, input this list 3141, output 4311. Okay, so we use the numbers here as digits. Okay, but now we use the number 1 multiple times. I have to check in a moment. Let's go back to it, but I first want to understand the Python test cases. Okay, so we kind of we create a permutation. This is called permutation. We permute the different digits to the output, and all of this is divisible by 3. I think there was this rule that if you just sum over the digits and the sum is divisible by 3, then the overall number is also divisible by 3, right? Let's check this. Divisible number by 3. Numbers are divisible by 3 if the sum of all the individual digits is evenly divisible by 3. Okay, for example, the sum of the digits of the number 36628 is 18, which is evenly divisible by 3, so the number 3627 is evenly divisible by 3. Okay, so this makes it more efficient later. So we can use this. Okay, then we have another one. We have like this list of 6 numbers, and now they took 5 out of them. And they took 5 out of them, and the 5 are divisible by 3. Why? Because 16, 18. Because if you add them together, the individual digits, then you get 18 as the sum. Okay, and we want to have the largest, right? So let's again read. Okay, the bunnies are given food on standard issue prison plates that are stamped with the numbers 0 to 9. And you need to combine sets of plates to create the numbers in the code. The signal that a number is part of the code is that it is divisible by 3. You can do smaller numbers like 15 and 45 easily, but bigger numbers like 144 and 414 are a little trickier. Write a program to help yourself create large numbers for use in the code, given a limited number of plates to work with. You have L, a list containing some digits 0 to 9. Write a function solution L which finds the largest number that can be made from some, or the largest number that can be made, so this is here, the largest number we want to have that can be made from some or all of these digits and is divisible by 3. Okay, sorry for taking time to reading this, but it's important that you understand the requested solution, the requested problem before you start coding. I mean, oftentimes many coders just want to get started, but usually, so in my experience, it pays to really understand and nail down the problem, even if it is like repetitive and boring. But if you understand the problem, then you will do the right thing. This is a very important for coding, in my opinion. So this is what I'm doing now. So we want to find the largest number that can be made from some or all of these digits and is divisible by 3. If it is not possible to make such a number, return 0 as the solution. L will contain anywhere from 1 to 9 digits. Okay, so we want to have the largest number, right? And I already have one solution idea. So So let's open the code share. Let's maybe first open the file solution.py. Okay, it looks like this. So we can edit this in a moment, and then we still have another file, right? Which we should read all files. We should have all the information before starting. Okay, in Java, blah blah blah, Python. Your code will run inside a Python 2.7 sandbox. All tests will be run by calling the solution function. Standard libraries, input/output operations are not allowed. Your solution must be under some characters. Okay, this is like nothing special. Good. So let's. You can always type help and then you can edit something. Okay, now we want to edit the file solution.py. And now the editor opens here, and here we code our solution. Okay, let's. Okay, our code comes here. So our list L is a list of integers, and now we want to sort. We want to have digits so we want to take all digits and combine them into a number. Okay, so one idea I already had. So if you have this, say the digits 9, 4, 3, 16, 2. Okay, so this one, so the sum of those digits is 13, 16, 18. 18 is divisible by 3, so therefore it would be a valid number. And now basically we can use all these digits and recombine them as we want. Okay, so we can use the same digits like this. We can do like 2, 3, 4, 9. So like actually any combination of these four digits will be divisible by 3, right? So we can divide all these numbers by 3. So in this case, it's best to sort them in a descending manner. If we sort them in a descending manner, then we will have like the largest number here. So this one will be the largest number, yeah? Because I mean we have the largest digit first. So so this contributes most to the size of the bigness or largeness of the number. Okay. So therefore, if we sort these numbers, so if you have some numbers that add up to 18, then we can simply sort them in a descending manner and get the largest solution basically. Okay. So now we need to find the set of numbers, or the sets of numbers that can be that together add up to 18, right? So the more numbers, the better. Even if we have like even if we would have smaller digits, like even if we could replace this 9 by say 2 numbers, 4 or 5, which are both smaller, but then still the overall number would be larger because we have more digits. So we want to have as many numbers as possible, even at the cost of trading in like bad numbers. Okay, how can we do this? So I mean, the trivial solution would be to go over all combinations of numbers, but this would be very, very, very computational expensive, right? If you take a like all these different combinations of the numbers in our list L and simply add the solution to the simply calculate the sum of those numbers. Okay, maybe first let's start with def check is divisible by 3. So this is a function we can easily compute, right? So we want to return true if the numbers in our list. Should this be a list or should this be an integer? It should be an integer probably, right? So we have an integer x. Let's call it. Let's just use n. Okay, so we have a number n, and we check if is the number divisible by 3. So now we take we convert the string. So even no matter how large the number is, we convert this number to a string. Okay, our input, I first have to check what is the input exactly. The input is a list of integers. Okay, so now we take an so now then we will have a sublist here. It makes more sense to have a sublist here. Okay, so the input can be if integer digits. Okay, now we simply assume this is an integer for now. We can adapt it later. Okay, so so we have an integer. Let's call it n again, and now we create, like, from this integer we create we return. So we convert it to a string. And then we go over all, so how do we do this? Okay, we need to sum over a list of things, or over an iterable, and for x in string for digit, and then we need to convert this digit to an integer. Okay. So this is a concise one-liner solution, right? So we use the generator expression here. We go over all digits in our string. So if we have, for example, a string or the number 1, 2, 3, then we have the string 1, 2, 3 here. And now we go over all digits like 1, then 2, then 3. We convert it to an integer. Okay, now we have a list or a sequence of integers. An iterable of integers, I should say, and now we sum over the iterable of integers. This will give us, so our app start drawing. Okay, so like we have this one 3, 3, 3, say, and this is our input. Now we go over, we create a sequence of those, yeah, by converting them to integers. So previously it was a string, now it's a sequence of integers. Now we sum over all of them. So the sum is 9, and now we check whether 9 is divisible by 3. So okay, so this is our sum, and if this sum is modulo 3, okay, if there's no remainder, then the result will be 0. Okay, so we check whether this result is 0. Okay, so we use the modulo operator, so we divide by 3 and only look at the remainder. And if the remainder is 0, then it is divisible. Otherwise, it is not divisible by 3. Okay, so we can use this function later in our solution. Okay, so again, now we have the list here, and we need to get all the different combinations of digits. Okay, like 4. So what if we have this, let's do some example work. Okay, so we say we have a list of some numbers. Now we want to start with all of those, right? So there, I feel that there should be a very efficient solution without needing to go over all permutations. Okay, so what initially we may start with all of them. Okay, so we just use all of them, then we sort them, and then we will check whether it is divisible by 3. Now if this doesn't work, if it is not divisible by 3, then we need to remove some, right? Now we can remove, like we have 5 different possibilities to remove a sequence from those. So we can, if we can remove any of those numbers and achieve like a number that is divisible by 3, I don't know. So how else can we build it? I mean, we can take this one, add them together. We can use some backtracking and so, but it may not be. Recursion may also work. You want to have the largest number that is divisible by 3 based on these digits. Okay, so we need to look at those. So for each number, either we take each number or we don't take each number, right? And then based on this, so based on the numbers we took, we can easily find the largest one. We simply sort the digits and convert it to a number and check whether this is divisible by 3. So we sort it because we want to have the 3 should appear in the beginning and the 2, for example, and the 1, like those 3 digits, they would together sum up to. And now if this is divisible by 3, then of course we can also add this one, right? Okay. So if we have a number that is already divisible by 3, then we'll just take it. We can immediately say that we take this number, right? Wrong. No, this is not true. Ah, yes, it is. It is true because it is already by itself, it is divisible by 3. So no matter which other combination we use, so even if we use this 9 here as a combination, we could always add this number later to increase an even larger, to get an even larger number. So if the number itself, the digit itself, is already divisible by 3, then we can simply like already decide to take it in our bucket, so to say. Okay, so this one will be accepted. This 9 will also be accepted for sure. So all numbers that are divisible by 3 will be accepted immediately. Which leaves us to with the numbers that are not divisible by 3. And now we need to recombine them so that they are divisible by 3, right? Now we can take, for example, how can we get those? So now we only have left 1, 2, 4, 5. So like we have 1, 2, 4, 5, 7, 8. These are the only ones we can have that are not like trivially in our bucket of numbers. Okay, so the idea is we put those numbers divisible by 3 in our bucket, and they are in the final number for sure. And now we only have those left. So an arbitrary combination of those numbers left. So now we can always, like if we add together, as it appears, if we add together any two of those numbers, then the result will be divisible by 3 somehow. So if you add 1 plus 2 divisible by 3, then we can add both numbers to our final list. Okay, so we can simply check them and check them. So if we have like 2 of them, if we have 4 5 or 2 4 5 7 7 8, all of them we can simply add together. So what about numbers that are not, so like 1 and 6 5 we can also, 1 and 8 we can also, but 1 and, okay, so if two numbers are beside each other, we can simply add them to the bucket. Then we can also add those numbers to a bucket, right? So 1 plus 5, 1 plus 8, and 5 plus 8. No, 5 plus 8 doesn't work somehow. Okay, there must be 2 in the... Okay, so this works. Okay, so in the first pass, so we have already added all numbers that are divisible by 3. Then we add all numbers that are beside each other. So they, like, if you have 2 numbers 1 2, we add them to the bucket. If you have 2 numbers 2 4, we add them to the bucket or so. And then if they are added to the bucket, of course we remove them from the list. So like, okay, let's again start this algorithm a bit. 5 6 7 8 9. Okay, like this. 1 2 3 4 5 6 7 8 9. So these are all possible numbers. Is a 0? Can there be a 0? Some digits from 0 to 9. Okay, the 0, we can always add the 0, right? So we will always like take all numbers that are divisible by 3 without remainder. So this one, this one, this one, this one in our first pass. Okay, so now of course this, I mean, this is assumed that this is our input list, right? So this is, now in this case it is trivial. Then we simply check whether we have 2 numbers, like could there be, can you construct a small graph? How can we do it? What if we have like 3 3 3 2 1 9 0? Okay, then we will immediately add this one to the bucket, 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 and now we add them together, the remaining, and we simply add them to the bucket. Okay, but how can we go over all different possible combinations? So remember, each number we either add then a number to the bucket or not. Because there can be many different combinations of numbers we add to the bucket. I mean, there can be like we may have 2 2 1 or so, and then we could add this packet to the bucket, or we can add this packet to the bucket, or even like this example, we have 1 2 and 4, 1 and 5, and now if we would simply add 1 2 to the bucket, then we could not add 1 5 to the bucket, which will be a larger number. So then we would have made a mistake. So being greedy with the remaining numbers is difficult. It's like not optimal. How can we do it? I don't want to use something like backtracking. You can also pause the video and try it yourself if you don't want me to ramble about the solution. Okay, so I don't want to do backtracking. Backtracking means that we try out one combination and then somehow down the line we realize that this combination didn't work, so we go back and try another combination, and we go back and so on until we have tried all combinations. This is, I mean, we can do it with recursion or so, but it may be inefficient. Okay, but otherwise we shouldn't do pre-major optimization, right? But is there something obvious that I miss now? If we so for the remaining numbers we can we construct a tree? We can use any number only once, right? The same digit may appear multiple times in a list, but each element in the list may only be used once. So we may not even need this function is divisible. Okay, so again we have, like, say we have 3, 2, 2, 2, 5, 1. Now, now of course the trivial case would be this one. Okay, we can simply add it to the bucket, but then we still have these remaining numbers left. And here we could add either 5 and 1 to the bucket, or we could add 5, 2, 2 to the bucket. And of course it's much better to add those to the bucket, but if you would have already added those to the bucket, then we would have a problem, right? So we want to add as many as possible to the bucket. So say we take all of them we haven't already added to the bucket, like here 11, 12. Now it turns out we can add all of them to the bucket. So what if we tried to add those to the bucket? And if we can't do this, because I mean the sum of those digits is not divisible by 3. If we can't do it, then we need to remove some. Which do we remove? Like in this case, of course, we cannot remove any, but if you have a 2 here, then this will still work, because those together will sum up. Those 3 numbers will sum up to will be divisible by 3. No, this also doesn't work. So we have to use all combinations somehow. It's not pretty, but I mean, somehow we have to test the different cases. We could use some kind of dynamic programming here, but I think this would be too hard for this simple challenge. Okay, so I first go with a trivial solution, and then we I may even adapt it later. Okay, so say we have number 4. Okay, how do we do this now? So if our solution R, so basically a simple solution is first we add all elements here. So we use a recursive approach. Yes, first we add all elements into our list, and now if this is not divisible by 3, then we will simply try to remove this element and apply the function recursively. Then we try to remove this element and apply the function recursively. Then we try to remove this element, apply the function recursively. remove this element recursively, and if you have the results of all of those, then we will check the largest one, right? So this would be so now we will have a recursive function is divisible by 3 for a certain bucket of numbers. So this, we won't need this one, maybe we will use it later. Okay, so I don't like this solution, but I mean, what's the point? So first we should have a simple solution and a trivial solution, and then later we can optimize. Okay, if calculate sum. So we have our sum s, which is this one. For digit in L. Now we go over all. So here in this one, we sum over all. So we calculate the sum of the digits basically. Yeah, we go over all digits in our list, and our list is a list of string digits. Okay, so this digit is a string value, so we need to convert it to an integer. Then we calculate the sum of this, and now we have the sum of those, and then we check if the sum of those digits is divisible by 3. Then, I mean, we're done. You can return true, else we want to have the largest. We don't want to have a truth value here. Recursive. Find largest bucket. Okay, so the purpose of this function is to find the largest bucket of digits that is divisible by 3. So remember, we don't care about the sequence yet. Later we will just sort this and find the largest sequence. Return L. I don't know if I have to do like to make a copy. Maybe I have to make a copy of the list later, but let's check. Otherwise, so in this case, if our sum is so if it is divisible by 3, then we can simply return L. Otherwise, we go over all elements in the list basically for x and L. Let's call it digit, and we create a new list which is basically now we try to remove one element. So we want to remove all elements from the list. So we create a copy of the list using slicing, and then we simply call temp remove the first occurrence of digit. Doesn't really matter. So each time we remove the same digit, even if the digit appears multiple times in the sequence, we remove the same digit, but it doesn't really change something. And we can later add a cache to make it more efficient. Okay, so then we remove the digit, and now we have the new list, which is a smaller list, and now we call Okay, now we call the function recursively. We don't even need the else branch here because I mean, if the if branch is fulfilled, then we will not enter the remaining part of the code anyway, because we simply return the result. Okay, so now now we try to remove the digit. We remove the digit from the copied list, and we call find largest bucket of our temporary list. And this is now also a list, right? So we will always have a list here, and let's store it in the temp variable also. No, so say we collect all of them basically. Now we collect this is now a list of lists which collects all lists, and we simply collected append this find largest bucket, so we simply append this solution, and now we have collected all of them. So let's comment this, find all smaller solutions, smaller buckets recursively. Okay, find smaller buckets recursively. Now we want to, yeah, we have all of them in the collected, and now we need to find the maximum. Okay, remember our find largest bucket function, it returns only lists that are divisible by 3. Okay, so this is like, it's an invariant basically. All of the return values are divisible by 3. So all sublists in the collected list are already divisible by 3. So therefore all of them are valid basically. Now we simply have to find the solution that is maximal. Okay, to find the maximum solution, we create a new function. We use it as a key function for the maximum function. So key takes a list and returns maximal value. So maximal, say, number from list, and for this we simply call the sorted function. So it's basically we sort them in descending manner. So we use the sorted function because it creates a copy of the list, and sorted L, and we reverse this basically. Okay, so we use slicing to reverse this list, because if we sort, then the standard sorting behavior is an ascending manner, but we want to sort in descending manner. So we simply reverse the list after we have sorted it. Okay, so now this is a sorted list, and now we want to like join them together and convert it to an integer value. So we use join sorted list, and we return integer of integer. Let's call it number. Okay, so this is our key function. So it input is a list, output is a number, and the number is like the maximum number we can get based on recombining those digits in the list. And now we simply max element. We simply need to find the maximum element, which is like we use the max function to go over all elements in the collected list. So which is a list of lists, and we use as key. We use our function, our key function. Okay, so digits to max number. Let's call it digits to max number. I mean, it's not very pretty actually, but okay. So I will optimize the code later. Okay, now we have the max element, and this is the maximum element as found recursively, and we now need to return the max No, this is not a max element, it's a maximum list. So let's call it the largest bucket, and this is what we return. Okay, so it's a bucket, and our solution is simply return. So do we even need this largest bucket function? Can we just use the use just the solution, I guess. Because no, our solution should be okay. There should be something else. So the result, if you read solution, the output should be like here, should be a number, an integer number, basically. Okay, return find largest bucket L. No, so let's call it max list. Let's call it X, and now this is a list of values still, but we don't want to have a list. We want to have a number. So we return the digits to max number L, because this is the maximum number X, because this is the maximum number we can get from this list. Yeah, we can obtain from the list, and this is what we want to return, the maximum number. Okay, so I will save the changes. I will try. So I will go over it once more in my own Python shell. Okay, so this is like we have a function that checks find max number. So this one finds the maximum number it can be generated from the list. It can be generated from the list, so we first sort it. So basically we assume, no, this is true for any list, even if it would not be divisible by 3. Okay, so it simply takes a list and it gives us the largest number. So if you have this one, so it takes this whole thing, a list of digits, and it gives us the largest number, like this one, 5, 3, 2, 2, 2, 2. Okay, so why? Because it will simply sort the numbers and give us the sorted result, basically. Okay, so so we could write this in a single line of code. Maybe it makes sense to. Yeah, it doesn't make really sense. I mean, yeah, we could write this in a single line of code, which would save a few characters, but I mean, who cares? Okay, so this function find max number, it works. Then we find the largest bucket given the initial list, and then we convert it to our maximum number. So let's call it, this function is called find largest number, find max number, and we also use it as a key function here. Okay, and now we calculate the inner sum of the list. Are the digits in the list divisible? If they are already divisible, then we return L, and then we find all smaller buckets recursively. And so we remove all the elements from consideration. But now here we don't have to remove all digits, right? This is the optimization. I mean, we don't even have to remove. So this number here will always be in the final list. So we will never remove the numbers that are divisible by 3. So this one will never be removed, and the 1 and the 3 and the 9 and the 6 and the 0, they will never be removed from the list. So this is like a low-hanging fruit which we can apply. For digit in L, if digit in, so only if it is like 1, 2, 4, 5. Now let's make it the other way. If digit not in 0, 3, 6, 9. This is simple optimization which we can use. Okay, so we go over all digits in our list, and if the digit is not one of those numbers, only then we remove the digit and call the function recursively. Otherwise, of course, we will never remove 0, we will never remove 3 or 6 or 9 from our list, so it doesn't make sense to remove those one. And yeah, and then we only remove the other elements, basically. We only try to remove the other elements. And now we simply remove all other elements that are in the list and append them to our collected list. So collected, let's call it candidates. I think it makes more sense to call them candidates. Let's call them buckets. buckets. Okay, and now the largest bucket then of course is a maximum of all these buckets, and we use the max number, the function find max number, to return the maximum solution. Fs modulo 3. So now we don't need this inner sum of elements, so we can simply use it, write it in a single line of code. It's a bit more efficient. So we sum over all all these digits, and try to divide it by 3. And if it is divisible, then we simply return the list, because then we don't have to remove any element, because it's already the maximal list. Okay, then we have a smaller, like then we will call this function recursively on the smaller list, where we have removed one digit. Okay, and then what may happen is, so we could add a cache to this, because sometimes we will, for example, do the following. Yeah, so we will remove some. So now we have the maximum thing. We try, is it divisible by 3? So in this case it's 10, 16. In this case so all of those numbers, they are not divisible by 3, right? So we have 5 plus 5 is 10, is 16. So this is not a valid result. So therefore we will try to remove this one, try to remove this one, try to remove this one, and then we will try to remove this one, and this one. But it is actually the same. I mean, we have already checked checked it. Yeah, it makes no difference whether we remove this one or remove this one. Okay, so they are really the same thing. So we can have a cache where we already store results that we have found, and like intermediate result, and use them if we have already figured them out. I mean, this would be a simple optimization, but I will maybe implement it later. Maybe let's first check whether our solution already works. We use like this one as an input. Print solution of this list, and then we print solution of this list. No, okay, copy. Okay, there was a problem, so when joining them here, so we join sorted list, so sorted list gives us sorted returns a list. The join expects an integer, but we have a string, but we have an integer. Okay, so we have an integer. This means we simply need to convert it for x in sorted list. Okay, so in our sorted list here we have an integer, of course. Yeah, we sort them, sort the numbers in our list, and therefore we have an integers, and we obviously cannot join together together integers. We can only join strings. So what does it mean, join? Here, if you have a list of integers like 1, 2, 3, 4. Now, if I first show you what I want to have, so I want to have a list of string digits, and now we can call the function join on the empty string, which means that we simply glue them together to this one. Yeah, so this is what we want to have, and so we join them, and now we convert this to an integer, like convert this 1, 2, 3, 4 to an integer. Will give us the integer number here. This is our max number, and this we use as a key for each bucket. Okay, now let's execute this. Okay, here we have 4311 and 94311. So it already works. It's also okay, pretty fast. Let's have maybe larger ones. Let's simply add a lot of numbers. So now we have a pretty large list, but it's very quick. So like, what happens if you have a very large list, like 1 for I in range? It will be very, I mean, it will be very fast, because so even if you have large lists, right? Because we don't have to do too many recursive steps. Okay, now it seems to be really slow. Okay, here it tries to remove all of them. Okay, this is not optimal. I mean, this code works, kind of, but it's not optimal. So let's just copy and paste this code for later use. The problem is that, I mean, we don't even want to remove we want to have a breadth first search rather than depth first search. So what we are doing now is we remove a digit and then we find the largest bucket from this smaller list. And if this is not divisible by 3, then we remove an element again. But then we have removed 2 digits, and this is not optimal, because if we have removed 2 digits, then we have not even checked removing 1 digit from the other one. So we first want to check whether we have first want to remove only 1 digit, check all of them, and only if you have checked all of them we want to go into the next level. So this way we can make it a lot faster, basically. I guess so. Let's go again back. I mean, we already have a solution. We could submit a solution and it will work, okay? So no problem. Everything from now on is just for fun. It's just for increasing our skill level. Okay, so if you at any time want to like pause or skip it, you can do. But you also have the option to keep watching. Maybe we will figure out a better solution. Okay, so this way we can find all smaller buckets recursively. We can so now say we have this whole bunch of ones. 3, 5 ones. Let's make it 7 ones. Now we try all of them. If it doesn't work, then we try to remove this one, try to remove this one, try to remove this one, and so on. So the question is there an iterative approach, not a recursive approach? Usually iterative approaches are faster. So there are two ways that I see. We can either start with 0 elements in the bucket and then we simply grow the bucket to have as many digits as possible, or we can remove elements to have and remove as few as necessary. So we can either start with all of them in the bucket and then we remove elements so that we reach the maximum bucket sum. So now, for example, we can remove, like in this case, we can remove really any, like this one. Now we have only 6. We have 6 elements, and now we can calculate the. Now this one is already an acceptable solution. And there won't be any better solution. So this is an optimistic approach. We add all elements to the bucket and then we only remove as few as possible. And then we have some values like 3 and 0 and 6, which we will never remove. And we will have elements like 5, for example. So like, which elements do we have left again? So let's make this again. So we have like 1 and 2, 4 and 5, 7 and 8. Now these are the elements we have, and sometime we want to remove those elements. But we need to remove some elements, but only sometimes, not like and then in which case, and we could even have multiple copies of them. So like if we add together 2 and 5. 9. So for those 4 numbers, so if the so I mean we are always in the modulo operation, right? So I mean if we take a whole bucket, calculate the modulo of this whole bucket, then we are in either we are in the class in the remaining class 0, or we are in the remainder class 1, or we are in the remainder class 2. So we are in one of those classes. If we are in this class, we are done. But if we are in, say, this class, this class 1, then we need to remove an element, and here we need to remove an element as well. So here it would be best if we remove. If we are in this class, we want to remove an element 1. Or an element 4, or an element 7. Because if you would remove one of those elements, then we would reach this class 0, which would be would be divisible by 3. Okay, then, but what if we are in this class 2? Like I don't know even how it is called in maths. It's like the remainder class or so. So we can so I mean if you have a bucket. So now this bucket of numbers. Now this bucket of numbers can either fall in this class, where like summing them up and dividing it by 3 will have remainder 0, or our bucket could fall in this class where it has remainder 1, or it could fall in this class where it has remainder 2. And if it falls in the class 0, then we are done. If it falls into the class 1, then we need to remove an element. Like we need to either remove the element 1, or we need to remove the element 4, or remove the element 7. And then we are done. Yeah. And if we are in the 2 class, then we need to remove either the element 2, or the element 5, or the element 8. And if possible, we want to remove the smaller one, right? Because then we will have a larger bucket, a bucket with larger numbers. So the bucket that results in a larger final number if we sort them and generate the number out of it. Okay, so if we can achieve this, then we are done. But of course, if we are in the bucket 2 and we only have like numbers 1, 4, 7, then we have a problem. Because if we remove 1, 4, or 7, then we will move from this bucket to that bucket. But then, as we have elements 1, 4, 7, we can, in one further step, we can reach this bucket. Okay, so this may be the thing. Okay, so no matter where we start, so in the worst case, we start our bucket as this remainder class. Okay. So if you remove, maybe it is mathematically like this, that each time we remove an element from one of, so I mean, what could happen? So in the worst case, say our bucket falls in this remainder class 2. This is the worst case, because if it falls in remainder class 0, then we are already done. Okay. So say it falls in remainder class 2, and then we have these elements. I mean, then we have these elements which we can remove 2, 5, 8. Then we are already done. Okay, so we only remove like 2. Sometimes it's never better to go into the so we can either go from. Now I see. Okay, so let's have a smaller graph. Okay, say we have a bucket, and with bucket I mean a list of digits. So it's like 3, 2, 1, for example. Yeah. So we have a bucket, and now let's add another element here, 2. Okay, and now we are in one of 3 classes. We are in class 0. We are in class 1, or we are in class 2. Okay, it's a simple automaton. Okay, so we have like transitions. So if we are in class 2 and we remove one element from our list, so then this can be, for example, then we will reach class 1 or class 0. So if we are in bucket 2 and we remove the elements, so we have remainder 2. Okay, so if we remove the element 2 or 5 or 8, then we will go from remainder 2 to remainder 0. Why? Because I mean we have removed this element, say, and so the result is now, if we had remainder 2, then we won't have a remainder 2, obviously, and we will have remainder 0 by dividing by 3, when dividing by 3. Okay, and now if we have, and then we will have if you remove like the 1, 4, 7, we will go into this class. Yeah, if we previously had the remainder 3, remainder 2, and we remove the element 1 from our bucket, then summing up all elements in the bucket and dividing by 3 will result in remainder 1. And removing element 4 and 7 will also result in remainder 1. And then similarly, if we are in bucket 0, we are already done. And we will never remove elements, as you know, elements 0, 3, 6 and 9, because those will be in the bucket for sure. And then if we are in remainder class 1, then removing, so we want to remove 1, 4, 7 to reach remainder class 0. And of course, if possible, we want to remove 1. If not possible, then we need to remove 4. Okay, so in this case, we need 2 steps. So if you have only 1, 4, and 7, so if there's one element, 2, 5, 8, if there's only one element in this remainder class 2, then we are done. We are just removing it, and it is the maximum. It leads to the maximum number of digits. So therefore, it's the maximum. And we try, of course, to remove the smaller ones first. But if there's no such element, this means that either we will have only those elements and then it is already done. No, then we would never be in the remainder class 2. Okay, this means that so if this is not possible to transition from the state 2 to the state 0, then we transition from the state 2 to the state 1. And I mean it's necessary because we won't have these elements. Otherwise, we could have gone from 2 to 0 directly. So we won't have those elements, and we won't have those elements, or we will have those elements, but those are not exclusively there, which means that we will have one of those 3 elements. And if you have one of those 3, then we simply apply this transition, going one step to the other state, and now we will have one of those. We will have removed one of those. Now there are 2 possibilities. The possibility 1 is that we will have, so we know that we don't have 2, 5, 8 in this state, because if we would have it in this state, we would already have it in this state. So therefore we could have gone here directly. So we will not have 2, 5, 8, and it also doesn't make sense to remove them if we are in this state. So if we are in this state and we still have one element from 147 left, then we go into this state and we are done with the minimum number of steps. But if this is not the case, so if we don't have 147 anymore because we have already removed it from this transition, then we cannot go even in we cannot enter this state here, this state 0. So everything we can do is so we are also not in this state where we have only 0369. So we don't have 147. So we need to have 258. Okay, so we have one element in 258. And if you remove one element from 258, and if we started in this state, we cannot have 258 at all. So if we went from here to here, then we cannot do anything about it. Then we will never. Of course this is now difficult to see, but so the only way we cannot move from here to here is if we have 258. If we start with one of those numbers, 258. So what happens? Is it necessarily true if we go from this state to? Let me think. So what's happened? 258. If you would remove one of those, we would simply reach this state here. So this, if we remove one of those, then we reach this state. And of course, we remove the minimal number here. So if possible, we remove 258. And now, we have the choice again. We can remove another 258 to reach this state 0, or we go back. Okay, so this is now we have a full automaton. Or automaton. I don't even know how it is pronounced. Okay, and basically we have all state transitions, right? So we know what to do in each step. We want to reach the goal state 0. So we have a simple automaton. So let's open the code shell again. Save copy as. Okay, so we have 3 remainder classes. So basically we want to implement this automaton, right? We have remainder class. So we are in a state. And our state is okay, we still need this number. Find max number. I do everything from scratch. Okay. Def get remainder class from a list. Okay, so what we are doing is basically we simply, so we don't care about the order yet, because we can later, if you have this bucket, we can later generate the maximum number out of it. Okay, now we have this function get remainder class. It gives us a remainder class of like which can be either 0, 1, or 2, and it's basically we create the number, and like we simply sum. This was what we already had in the previous example. Integer x for it's already an integer, right? X for x in L. So now we go over all integer values in our list and sum them together. Okay, so it's okay. Now we can simply sum our list, and we return the sum of our list modulo 3. This is the remainder class. We don't even need this function. It's trivial, right? Okay. So our state is this one. Let's call it state, and we have remainder class. Okay, we have a state. This is our current state, and now we need to model the state transitions. So we have a bucket, and in the bucket we put all elements x for x in L if x modulo 3 equals 0. Okay, here in the bucket we already throw all elements that are already divisible by 3. This is a small optimization. And then we have the candidates x for x in L if x modulo 3 larger than 0. So if it is 0, then we will have the bucket, otherwise we have the candidates for the bucket. And now we simply copy this state here. State is sum of the candidates modulo 3. This is our remainder class. Let's do it like this. Okay, now we will have state transitions. We will remove candidates from our list. Yeah, while while some candidates modulo 3 it's our state, yeah, while state larger than 0, we do something and then we recalculate our state. Our state is again the sum of candidates modulo 3. And now here we remove an element from our candidates. And which one we remove, I mean, now it depends. We can either be in state 1 or 2. So if state equal 1, then we do something, remove like 258, or move to state 0, or remove 1 for 7 and move to state 1. Okay, else state, else, I mean, we know that our state is larger than 0. If the state is 1, then we do this one. Otherwise, we know that the state must be 2. Because the state can only take the value 0, 1, or 2. So we know it is 2. Else, elif state equal 2, so that we know that it is actually 2. Okay, now we remove 1 for 7 and move to state 0, or we remove 2, 5, 8 and move to state 2. No. No, actually this one was state. Okay, so I made a mistake, but I will correct it in a moment. So let's first copy paste both of them. Okay, so if you are in state 1, then we need to remove 1 for 7. 1 for 7, as you can see in the state machine here. So here you can see, yeah, this is our state machine. And if you are in state 1, then we remove 1 for 7 and move to state 0. Otherwise, we remove 2, 5, or 8, and we move to state 2. If we are in state 2, then we remove 2, 5, 8 and move to state 0, or we remove 1, 4, 7 and move to state 1 again. Okay, so and we always try to move to state 0 greedily. And I think this should give the solution, I'm pretty sure. So like probably I can write it a bit more concise in a moment. So say we have okay, if so like a very dumb approach would be this one, if 1 in L or 4 in L or 7 in L, but I think we can use simple intersection. This is even more efficient. So if we have the set of L, so now a set intersection was again, so let's check set intersection Python. Set intersection so I know that there's a shorter way of intersecting two sets and just using this intersection function. Alternative. So, but they don't have it here actually. So set intersection S and T. Okay, it's as simple. Okay, so here we create a set from the list, and we use set intersection, so this and symbol, and now we create a new set, 147. Okay, and if this is non-empty, then we want to do this one, yeah? We want to remove 147 and move to state 0. Else, we want to remove 258 and move to state 2. So here we have basically, we create a set from the list and we only check whether those 3 elements are in our list. Yeah, if one of those elements is in the list, we basically want to take the minimum. We want to take the minimum of those elements and remove it. And we move to state 0. Okay, so we have L remove minimum 1. Is it even a function remove? I think so. 147. So we remove the minimum of 147. No. I mean, not the minimum of 147. It's always 1. But okay, so now we let's simply have a variable called intersection. These are elements that are in both sets. And if the set is non-empty, we will enter here, this part. And now we want to remove the minimum of our intersection. So these are the elements in 147 that are also in the set, in our list L. And we want to remove the minimum of those elements from our list. And reach the state of state 0, right? Our state is now 0 because we have removed this part. Okay, so we have done basically this here. So we are in state 1, and we calculate we check whether we have elements 147. If we have element 147, we want to remove them and move into state 0, and we are done. And otherwise we are, so let's remove this. We don't even have to tell them in which state we are, because we calculate it later here. So it will figure out the state automatically. Okay, otherwise we remove the minimum of 258. Otherwise the intersection is empty. This could also mean that the list is empty, right? So I mean, of course, we need to check whether the list is empty at each point. Basically, why not checking while candidates, while we still have some candidates? Now we iterate this procedure as long as we still have candidates left. And I mean, if we don't have candidates, we don't want to remove from L, we want to remove from candidates. That was my mistake. Okay, now and also here set candidates. I hope that you got this right. Okay, so we want to remove from the candidates and the minimum of the intersection. Otherwise, we want to remove 258 and move to state 2, because we know that candidates, there's still an element left. So in each time, I mean, there's still at least one element, and the element is not 0, 3, 6, 9, because we have removed all of them from our candidates. Okay, so it has to be either 147 or 258. And if it is 147, then we will go into this branch. Otherwise, we go into this branch and we are sure that we can remove one. So candidates, remove minimum of set candidates Okay, let's use this intersection set candidates and 258. Okay, now we want to have the minimum of the intersection. Okay, now this is we can do the same thing. Okay, now we want to remove the minimum of this intersection between the current candidates and the values 258. So for example, if we have values 2 and 5 in our candidates list, then the intersection will be 2, 5, and we want to remove the minimum, which is 2. And now you can already see that we, like in both branches, we execute this code. So basically we could like use this code only once. We remove the minimum from the intersection, and in the branch we simply calculate the intersection. So now we take this one and move it here. So now our code becomes prettier and prettier. Okay, so so if you are in state 1, then okay, no, I don't. I have to use it here as well. I have to use it. I have to compute it once, and only if it is not empty. If it is empty, only then we want to move. So if we are in this state, and only if the intersection is empty, we cannot move into this state. So we have to move into this state too. We have to move into this state by removing 2, 2, 5, or 8, and it is possible for sure. And so only if not intersection, if our intersection is empty, we calculate a new intersection, and then we remove the minimum of this intersection. Okay, in both cases we remove the minimum of this intersection. And here we intersect the candidates, and here we intersect the candidates with 258. Okay, now this makes sense. Good, and in the other case we are in state 2, and if we are in state 2, we could either like move to state 1 by removing 147, or move to state 0, which is our preferred way, which by removing 258. Okay, so I guess we will have something similar as here. So I will just copy paste and adapt. Okay, so we have intersection. We again calculate the intersection of our candidates that are currently in our sets, and 1, 4, and here we want to have 258 as priority. Yeah, so we want to try to remove 258 if possible, to move into this class 0, in this remainder class 0. If we do this, so if we can, then we simply take the minimum, remove it, and move into class 0, and we are done. If we cannot, then of course we want to recompute, and then we need to like remove 1, 4, or 7. Now if so we calculate the intersection between 1, 4, 7 and the candidates. So I want to get all those numbers that are either 1 or 4 or 7, and then we simply remove the minimum of this intersection, and we move into the state, into the next state. Okay, so if we are in this class 2, in the state 2, then we move like this into our state 1. Okay, so and then we simply in each loop iteration we recompute the state, and we repeat this until we reach the point where we are in the correct remainder class. Yeah. So in each step we change our remainder class. So if we are in 2, then next step we will be in either in 1 or in 0. If we are in 0, we are done. So only if we move to 1, we are not done yet. And now it could happen. So is it possible that we move from 2 to 1 to 2 to 1? This may be possible. each time we can move to state 0, we will, greedily. So we will always have the maximum number of digits if possible. But if we move between states 2 and 1, then at one point it will be empty, and this means that we haven't found a solution. Okay, and so now if we haven't found, so like if candidates, if there are still candidates, then we can add them to the bucket. Basically we can bucket extend candidates, so we can take all candidates and that we have not yet removed, put them to the bucket, and then we calculate the minimum as we have done previously. Okay, so so like in this FooBar we have the digits to max number, so we basically sorted. Let's copy this. Okay, so we take a list and we return the maximum number from this list. Okay, we first sort them, then we reverse them to sort in descending manner, then we join them together. So we have the sorted list, but we need to like, we can only join together strings, so we need to for x in. Okay, we need to do this. Okay, the string conversion, this was a mistake previously, so we convert it we convert each element in the sorted list to a string and return the number. Okay, so this one return the maximum number from the list. So basically we don't need this function, yeah, just do it in one function. So we calculate maximum number from the bucket, sorted list, we take the bucket now, and we go over all of those and join them together and return the integer value. Good. So this should work. Let's check whether we can still make it prettier. So we have state equals 1. So because we have some redundancies here, right? Like in this section. While we have candidates, we check if state equals 1. Okay, here you see candidates we have in both if branches. We have candidates remove the minimum of the intersection, so of course we can take it here and move it out. Here basically we find number to be removed. Find possible numbers to be removed. And we then call it, maybe don't call it intersection, but to remove. Okay. So if state equals 1, then to remove is this one. Else, if the state equals 2, if the state is 0, so if state equals 0, then break. Okay, so I mean it's not pretty to do it like this. while state is larger than 0 and we still have candidates. And here it may happen that the bucket is empty. So if not bucket, if our bucket is empty, then we, of course, we don't have any, we haven't found any solution, right? Okay, we have so if it is empty, then we should return 0 as a number. If it is not possible to make such a number, return 0 as the solution. Okay, so now we don't have to differentiate this. We simply calculate the maximum number of the from the bucket. We sort over all elements in the bucket. Number is the join number and then integer number if number else 0. Okay, so we use the ternary operator, so we check if the number, if it is only if it is an empty string, it will evaluate to false. If it is an empty string, this means that our bucket was empty in the first place. So we have sorted an empty list, so to say, and reversed it. So we did nothing, we still have an empty list. Now we join together the empty list. So we join an empty string which is an empty string. Only then we will have then number will be an empty string, and if in this case we will return 0, otherwise we return the integer of our non-empty string. Okay, so this way we have made sure that this case is still valid. Okay, so now our code is, I think it's pretty good already. So we recalculate the state in the end because it may have changed after removing something. We from the candidates we have if not to remove, so we have a lot of set candidate conversions here. Not to remove, set candidate. Okay, I guess we could make this more efficient, even more concise, but I think it's already fine. Remove. Move to new remainder class. I mean, basically, we don't even need this bucket and candidate differentiation, right? Doesn't make sense to differentiate between those, because here we will only remove 147. And here we will only remove 258. So we would not even consider removing 0, 3, and 6 and 9. So therefore it doesn't make sense to differentiate between candidates, to even have these candidates. We only have the bucket. This simplifies the code even more. I mean, sum of the bucket, then we don't have these candidates. And bucket. We don't need to add them again back to the bucket. We only have the bucket. Okay, so we saved a few lines of code. Good. So now we only have the bucket, and we find possible numbers to be removed. Transition between remaining classes. By removing numbers. Okay, if our state is 1, we remove this one. Okay, if not, remove. So here, this is where we calculate to remove. Then we remove the minimal number. Remove minimum and move to new remainder. Some bucket is, and then we calculate the maximum number of from the bucket. Okay, we again have this sorted list thing. We sort the list and then we join the numbers together. And then we convert it to an integer, and that's it. So this should work. So let's try it. Let's try the test case first again. Print. So I have already here, I have 2 test cases. So this should be really fast now. 3 and 0. Okay, so it was very fast. Previously, it took us forever to check this. Okay, but it tells us that it is not possible for I. This is clearly wrong. We remove 1. Okay, sums. Updating fade FooBar. Okay, so what is our solution for copy? Print this one. Okay, bucket remove, then we move the state. If we are in state 2, we want to remove 258. If we remove 258, then we are in state 0. While state. Okay, if our bucket is empty, then we will not enter this loop. If it is empty, then we will not enter it, and the result will be like an empty, will be 0. Otherwise, the bucket won't be empty. And then we check, we repeat this as long as the state is larger than 0. We sum over all elements in our bucket. Oh, okay, now our bucket should be the same, the whole list, right? So, oh, no, this was a big mistake now, very big mistake. So basically we don't have a bucket. I want to operate on a copy of the list. Let's make a copy and store it in the list. Don't modify existing list object. Okay, so now we create the bucket, and previously we had included only the elements 0, 3, and 6 and so on in the bucket. Okay, very big mistake. But now we want to have all elements in the bucket. Okay, so we simply create a copy here with slicing. We create a copy of the list, and now we can simply remove the elements. Okay, here it still takes some time, but I guess it should be. I mean, it is 1 million elements. So if this terminates, then I'm really happy, because then it's really efficient. Okay, but 4311, I think it's already like 4311 was a required solution. 94311, it's also a required solution. So this seems to work. It's still computing here, but it has found a number. Okay, so it's a squeezed output is very long. It's 12,500 lines. So a lot of. Basically, yeah, it's a lot of ones. Basically, this all this joining stuff, it's very inefficient. Yeah, but it makes sense. We simply remove one character, like 1 1, and then we move into the remainder class 0, and then this is a result. So if you have 1 million ones, we remove 1 1, and then we are in the perfect remainder class, and that is divisible by 3. Good, so it seems to make sense. Let's check another extreme case where we have like an empty list. Okay, I will remove this extreme one. So we have an empty list, and the result will be 0. So what happens if we have a list with only elements where it doesn't work? I mean, like 1 1. It will never be in the remainder class. Then we also have 0. And what else? So now it's really blazingly fast. I love this solution. This solution works beautifully. Okay, so again, why does this solution work? We have these 3 classes. So this is a solution idea. We have this automaton, and we add it to the so we move from remainder class 2 to remainder class 1, and from remainder class 1 to remainder class 0, and we have these transitions. Our goal is to go as fast as possible to remainder class 0. And yeah, we do this by removing either element 2, 4, 5, or 8, and if possible, we want to remove the minimum of those elements, because then this leads to a larger overall number, and we want to maximize the number, right? This was in the output. Okay, so should we verify? What do you think? Should we verify our solution and submit? So let's copy paste this code, put it here. Remove this part and save it. Good. Now here, if you type help, okay, we have already typed help. Then you can use verify and verify your solution. Okay, we type verify solution.py. It verifies the solution. it passes all test cases, so we can submit the solution, submit solution.py. Do I want to have anything before submitting? So I think it's fine. Are you sure? Yes, we are sure. It submits the solution. Yeah, and we reached level 3. So we can refer a friend, basically. Nice. This is single-use code, so choose wisely. I already know which friend I refer. Type request to request a new challenge now. Okay, so I will refer my my friend and a friend of mine. Okay, so let's make a screenshot here. Okay, good. So so far so good. Sorry for this. And so let's store it somewhere in the mini course. Let's call it. I won't save it. I will just copy it and move it here. Okay, so please know it was really, I mean, I did this, all of this ad hoc. And yeah, now we can request a new challenge, and we can come back later at any point. And I will go on, like next time I will share level 3, hopefully. So this time it took me really almost 2 hours to solve the challenge. So challenge got harder. I mean, I had a ready solution maybe after half an hour, the brute force approach, but now the solution we developed over time with this remainder classes, it's much better, it's much more efficient, and it probably has linear runtime. It has linear runtime, and it's a much nicer solution. Okay, so thanks for watching this video, and see you in the next challenge, level 3. Bye.